Let's continue our discussion of the state-of-the-art thin-film silicon multi-junction PV devices. In terms of bandgap energy utilization and reducing thermalization losses, the amorphous silicon nanocrystalline silicon is not the best choice. The triple junction based on amorphous silicon germanium and nanocrystalline silicon would in principle do a better job. It will result in the highest initial conversion efficiencies. The company United Solar in the United States demonstrated this already in 2011 using an NiP triple junction structure. The substrate was a zinc oxide silver back reflector deposit on a stainless steel substrate. An additional innovation introduced in this triple junction was the bifunctional silicon oxide layer between the middle and the top cell. It serves as the N layer of the amorphous silicon germanium middle cell, and it serves as the intermediate reflective layer between the amorphous silicon germanium middle cell and the nanocrystalline silicon bottom cell. The combination of innovations resulted in a reported initial conversion efficiency of 16.3%. A challenge, however, is that 75% of the power of the device is generated in the amorphous silicon and amorphous silicon germanium, both suffering from the Stable-Wronski effect. Therefore, this triple junction has a higher sensitivity to light-induced degradation. The stable efficiency is therefore lower than the record value of 14.0% of the amorphous silicon nanocrystalline silicon triple junction. Let's integrate an additional junction. So now we have a quadruple junction or a 4-junction device. Here you see an example of quadruple junction in a superstrate configuration that is processed at the Delft University of Technology. The quadruple junction is based on the following materials going from the top cell to the bottom cell. First, a high bandgap material based on amorphous silicon oxide. Secondly, hydrogenated amorphous silicon. Thirdly, hydrogenated nanocrystalline silicon. And fourthly, hydrogenated nanocrystalline silicon. A modulated surface texture approach has been used to facilitate the light management and allow high electrical quality for the photovoltaic active materials. An initial efficiency of 11.4% was obtained using this complex device configuration. The further optimization still requires a lot of work to achieve better efficiencies than for the triple and double junctions. Another example of a quadruple junction is processed at Helmholtz Zentrum Berlin in Germany. The cell is based on amorphous silicon, nanocrystalline silicon architecture. A record stable conversion efficiency of 12.4% was obtained. The initial efficiency was 14.0%. Note that this cell was basically a first attempt and was therefore not optimized yet, so further significant improvements for this device concept can be expected. Let's summarize the presented record results on thin-film silicon monolithically integrated PV devices in this video. I will summarize the results using this graph. On the horizontal axis, you see the number of junctions integrated in the multi-junction device. On the vertical axis, I will plot the external parameters corresponding to the record-performing multi-junctions discussed. The open circuit voltage is logically increasing with the number of series connected junctions in the device. Note that the open circuit voltage of the micromorph cell is 2.5 times larger than that of the nanocrystalline silicon single junction cell. This is a result of the introduction of the high bandgap of amorphous silicon in reference to the lower bandgap of the nanocrystalline silicon used in the single junction cell. With a larger number of junctions, the current density is decreasing. The photons need to be equally distributed over the junctions to generate an equally distributed current density to guarantee a current match cell. If we look at the record efficiencies, the effective photon utilization can be expressed by the total generated current at all subcells that contributes effectively to the cell current. This is the given number. As you can see, the nanocrystalline silicon junction and the amorphous silicon nanocrystalline triple junction have a good photon utilization. However, the record micromorph is not optimal. The triple junction cell shows a better photon utilization, whereas the quadruple junction shows a worse photon utilization again. This shows that the record tandem and quadruple junction PV cell is either far from the current matching, or the cell architecture still suffers from parasitic absorption losses. Note that both single and triple junctions are solar cells in the substrate configuration, and the tandem cell and quadruple cell are in the superstrate configuration. This suggests that at least the parasitic absorption losses in the superstrate cell configurations play a more dominant role in quenching of the photon utilization. The main reason is the front electrodes based on TCO. We can demonstrate that using the results presented here. In the micromorph device developed at Delft University, using the high transparent and conductive front electrode based on a double layer of hydrogenated indium oxide and intrinsic zinc oxide, the parasitic absorption losses are in the front electrode significantly reduced. The achieved short circuit current density of 14 milliamps per square centimeter is significantly larger than the current density achieved in the record tandem cell. If we look at the record efficiency, we see that the triple junction configuration is outperforming the other configurations. The results suggest that for the double and quadruple junction, higher values can be obtained when applied using the substrate configuration or using alternative TCO front electrodes. The fill factor differs not much. It for a large part depends on the current mismatch between the subcells. The quadruple solar cell need to be further optimized. The results are preliminary results. This is still work in progress. The inclusion of low bandgap materials below that of nanocrystalline silicon, like nanocrystalline silicon germanium or germanium tin alloys, would further improve the efficiency of thin film multijunctions based on the 4 valence elements like silicon, germanium and tin. Important to address at the end of this week is that by scaling up from lab scale devices to a PV module, we have seen that conversion efficiencies only relatively drops by 2%. In addition, flexible thin film silicon modules are already available on the market. In the final week, I will discuss in great detail the upscaling potential of all PV technologies that we have discussed or still will discuss in this course. Next week, my colleague René van Zwaay will discuss the CIGS and cadmium telluride PV technologies. These are the thin film technologies with efficiencies similar to the multicrystalline silicon solar cells. See you next week.